All right, hello and welcome to this video. We are going to be going over, before you continue watching this video, let's make sure that this video is made for you. We're going over SVM machine learning models. So the algorithm, the SVM algorithm, what that is. We're also going to be going over some matrices, some confusion matrices to plot the accuracy of our model. We're also going to be using the iris dataset. We're also going to be using pandas in Python. If this all applies to you, you can certainly continue watching the video. We're going to be covering what a support vector, so what SVM is, and then we're going to be covering some data engineering, cleaning up the iris dataset so that we can use it to make our SVM models, and then we're going to plot our confusion matrix charts to show pretty good visuals of what it did, how accurate it was, and so on and so forth. So let's get started. This video is for you. Let's start off with support vector. So this SVM model. What an SVM model is it's not a unsupervised learning thing. It doesn't cluster. It doesn't create clusters. What it does is it just creates a decision boundary. This yellow line is a decision boundary. So is something a 1 or a 0, basically. I don't know. You want to just make a boundary between those two sets of dots. We'll call it class 1 and class 2. Now, usually with one of these boundaries, it would put into effect the weight of each of these dots. But with SVM, these support vectors here, the ones in purple, are the only ones that are dictating where that line goes. So if I were to remove the red dots without purple circles around them, that yellow line, that decision boundary, would actually not move. But if I removed a red dot that has a purple circle around it, then that line would move. So the whole point of support vector machines, SVMs, is it creates these support vectors and bases its decision boundary on those only. Okay, so moving on, let's close this. So what we're going to be doing is, oh, sorry, I have my data already loaded. I want to go from scratch here. So here I have my Jupyter Notebook open, and we're going to be using the iris dataset. If you know what the iris dataset is, it's a dataset of iris flower information. So like their sepal length, their petal width, and then the Y value, so our target is the actual class name of those flowers. I think there are 3 of the flowers. I just took a look at the iris dataset before starting to make this video because I actually didn't know how many flowers were in this dataset, so but now I know. Let's figure it out. So first we're going to import pandas because we're going to be using pandas to clean up our data. And now we have to import the iris dataset. So from sklearn. Let me press tab here. Yeah, datasets, import. I think it's load. Yeah, so if you type in load here, all the datasets that come with the sklearn, we're going to import load iris. So now that load iris is in, we're actually going to save it as a variable. So the variable we're going to save it as is just simply iris, and we're going to do load underscore iris and put that right in there. Let's take a look to see what that actually gave us. So we see that the iris dataset here comes with, you're going to see a few things. It's a dictionary. The first key is data, and it looks like this is all the data for our actual flowers. And if you take a look at the first few here, these values are pretty, they're pretty similar, right? Like 0.2, 0.2, 0.2, 0.2. So I made the assumption prior to making this video that these first bunches of flowers were actually the same flower. And I was right. So it seems like this data set is actually in order. What we don't see in data is the actual name of the flower beside it. So this is just the X information. So this is just the data for the flowers. But if we scroll all the way down, you're going to see the target array. Now this target array is actually each flower. So if you see target names down here, it'll show array setosa, versicolor, and virginica. So those are the 3 different classes of iris flowers. And here you'll see class 0, you'll see class 1, and you'll see class 2. So those first bunches of flowers that we saw that had similar structure were all classified as setosa flowers, setosa iris flowers. So what we're going to do taking a look at how this is structured is we're going to create a variable or data frame called x, and we're going to store data in it, so all this info. And then we're going to create y, which is our target array, and we're going to throw y in there. Yeah, we're just going to throw y, and we can actually change them to the target names. We'll see what we want to do exactly there. But let's get rid of this. Pretty sure I know how this all works now. So let's go x equals, and I'm going to do iris.data. So I'm going to save that, and then let's print out x to see what it looks like. So only the data now from the iris data set is stored into x. But it doesn't look like a pandas data frame. So how do we make x a pandas data frame? How you do that is you do pd for pandas dot data, make sure the d is capital, frame, make sure the f is capital, and then we're going to throw x in there. So when I run that, you see this. But unfortunately, this doesn't save x as a pandas data frame. X is still this, as you can see here. So what I want to do is x equals pandas data frame x. And once I run that and then show you x is now stored as a pandas data frame. And we can check that by typing in type x, and it'll show you now that it's a pandas core frame data frame. We don't need that right now. That's all good. But taking a look at x, let's do x.head here, and we can see that the names of these columns are kind of funny. They're just numbers, right? They're index numbers. What I want to do is I want to make these numbers the names of the, what does it say? Sepal length, I think, was 0. Let's check. So what did we do here? We did, I'm going to keep that like that. Let's go into the next thing. So let's do iris.data again to take a look. No, let's just do iris again. And let's take a look to see where the column names are stored. Okay, it looks like we have here target underscore names. So what I can do here is let's add a cell above by highlighting this cell by clicking on around here and then pressing the letter A in Jupyter Notebook. And what we can do is we can do x dot columns. And what that does is it just, like, here's how many columns you got. It starts at 0, it ends at 4, and every one step, like it's 0, 1, 2, 3. So we want to make that 0, 1, 2, 3 equal to target names here. I want to grab this array that says Setosa, Versicolor, Virginica. I could technically copy that and paste, and I could technically paste that in there, but what I want to do is I want to do iris dot, I think I can do target dot names. We'll see what happens there. So that doesn't work. Array object, yeah, names, okay. Target underscore names, that's probably what I messed up here. Let's see why I didn't do that. Expected access of 4 elements, but new values have 3 elements. Oh, that's strange. Let's take a look. Oh, you know why? Because I'm using the actual names of the flowers. What I need to use is I need to use the, where are the column names? Does it have column names here somewhere? What is it here? Sepal length, sepal width. Very strange. I'm going to have to probably name them myself. So I know that the first column, let me just get rid of this to make it nice and clean. The first column is, so x.columns equals, let's do this, sepal length. So yeah, sometimes when you're doing data engineering, you have to kind of hand bomb stuff like this if you can't find exactly what you need. Even if what you need is there, sometimes you just want to put it in manually, see how it goes. So this is sepal width. I know that's the second column. The third column is petal length. I think the last column is petal width, I think. So I just ran that. Now let's take a look at X again and see. So it seems like our columns were renamed just ever so nicely. I'm going to get rid of that again. But now I want to add on that, you know, that Y column there? I could technically add on the Y column onto my X data frame. Now I don't want to do that. I just want to save Y as a thing here. And what was it called again? Let me just take a quick look. Iris. Let me scroll down. It's just called target. So I do iris.target. What do I get? Yeah, so I want to make, let me copy this. I want to make Y equal to iris target. Okay, so I can get rid of this by clicking on it and double tapping D. Nice and clean. And let's see what Y looks like just to make sure. So now our X is saved as our data set. Now Y is unfortunately just an array. Can we keep it as an array? I think so. We'll see what happens there. But I could technically make it a Pandas data frame if you needed to by pd.dataframe and making that Y. I'm not going to do that, but just so you know, as a reminder, that's how to do it. So I have my Y, which is my target. Then I have my X, which is all of my data. And, well, let's move on from here. Let's take a look at my, Let me take a look at something very, very quickly first. I want to do Y. I want to do iris.class. Let's see what that does, just to make sure it doesn't do anything. I think I saw class in there with a capital C. No, not there either. Okay, that's fine. Okay, so now let's move on to creating our train test split. If you do machine learning, you know that you want to split your training data and your testing data separately so that your machine learning can have like a textbook to train on, which has the questions and the answer key. But then when you're testing your model to do predictions, you're only giving it a test with no answer key. So let's split those all up. So you want to do from sklearn, and it's called .model selection. We want to import train test split. And then we want to type in all four of our things here. You want to do train, you want to do X test, and then you want to do Y train, and then Y test. So those are the four things that you want to create with train test split. Now it equals train test split, but we have to put in the parameters here. It wants to know, if I hold shift and press tab, it's going to want to know, oh, let me see if I can show you that better. Shift and tab. No, it didn't work. That's fine. So it'll show you if you did press shift and tab on your Mac or your Jupyter Notebook, it'll tell you okay, what it wants in here. What it wants is your X data. It also wants your Y data. Oh, I didn't put a comma there. It also wants to know how you want to split it. Do you want to make it a 50-50? Do you want to make it a 60-40? So what we want to do is we want to do test size equals 0.25. We'll do a 75-25 split. Usually it's 70-30. Sometimes it's 80-20. Let's do somewhere in the middle. And then you have random state. Now, if you know what a seed is like in Minecraft. When you get a seed and you put it in when you create a new world, you get a map. And the map it looks totally random, but it's not random at all. There's a seed that you put in to create that world. Now, if you were to delete that world, create a new world, and put in the same seed, you'd actually get that same exact map again, block by block. Python does the same thing here. It's called a seed, or in this particular case, in train test split, it's called random state. So if we both put in 42, me on my computer and you on your computer, we will get the same results moving forward. So let's run that block and continue a bit. Let's move this up. Okay, so now that we have our random state set, everything seems to be good. These four variables are now set and ready for us. So let's start by importing our SVM. So from sklearn, because that's what we're using, import SVM. And then while we import SVM, now the computer knows, okay, well, what kind of SVM do you want to use? Like they're called hyperparameters. It's like SVM can run a certain number of ways. How do you want to run it? Well, let's only work with one particular hyperparameter today. The hyperparameter is called a kernel. Kernels do different things. It makes the SVM library, it makes the SVM model look through things a little bit differently. I'm not going to get into the math today and dimensionality today, but let's create our variable. We'll call it CLF classification and SVM.svc, which is how you call this bad boy right there. And we're going to use kernel equals, we'll do poly, which is your polynomial. Now, if I shifted and tabbed here, usually it doesn't show it for some reason because I'm streaming, but it'll show you the basic help function, and it'll give you all the parameters that you can put in here. One of them is one of them's RBG I could do, but one of them's poly. Maybe we'll do both in this video. So let's run that. Now CLF variable is now saved as an SVM. We can actually test that. If I type in CLF, it'll say it's, sorry, as an SVC. It is an SVC model, and it uses the kernel that is polynomial. So it's using the poly kernel. Okay, no problem. We don't have to check that anymore. So now let's make our CLF, let's make it smart. So we're going to do CLF.fit. And what fit does is it's like giving your CLF model a textbook. The textbook should have two things. It should have your training questions, so like your sepal length and your sepal width and all the data, your X data, X training data. But you're also going to give it the answers. You're also going to give it an answer key. And what it's going to do is it's going to learn. It's going to open up that textbook. It's going to look through the training data, and then it's going to cross-reference against the answers. Y is the answer data, the target data. So let's run that. And that ran very quickly. So we have an SVC kernel poly. We knew that from before, but the difference is this time it's smart. So now we're going to do our actual test. I think we're ready to give it a test. So if we do clf.predict, press tab here, clf.predict is, hey, here's a test. What's on the test? Well, our X test set. Are we putting in the answer key? No, we're definitely not. We're just making it test. And we want to see what answers it spits out. Now, how do we do that? Well, let's save its answers right here in the Y prediction variable. So this is the predict. So give me the answers to X test, Mr. CLF or Mrs. CLF, since you're so smart. Give me the answers to X test and save them here, please. Okay, so if I run that, I don't know if I ran it or not. Yeah, now I did. Now that I ran it, it's smart. So I can technically type ypred and see what it put in for answers. And if I were to do y test, I could see the y test answers and the y prediction answers. Now, sometimes these are like millions of answers, but we can pretty much eyeball it. Let me see here. I think they may have gotten 100% of their test. Let's see. I think this is kind of cheating. I'm going to get rid of these. And let's make a confusion matrix to see how well it actually did. So we're going to do from sklearn.metrics right here. We're going to import confusion matrix. And what that is it allows you to put in the y-test answers and the predictions made by our model, and it cross-references them. It shows you, how many did they get right. So here I'm going to do confusion matrix, and then I have to put in my y-test and my y-hat, or my y-predictions. And when I run that, you see that it almost got perfect. Look at that. But there's one value that it got wrong. No, I deleted it. If you really looked at it, you would have seen one answer wrong. Now, how do I know that these are the right answers? That's a good question. You know what? Why don't we visualize it a little bit better? Let me just raise this up a touch. We're going to import matplotlib so that .pyplot as plt, so we can plot a better looking confusion matrix with like some labels, so you can see what their guesses were, like the true labels of the names of these flowers. And it's as easy as from sklearn.metrics, you import, it's called plot confusion matrix. So now that you have that in here, you want to call plot confusion matrix, and you want to put in your model. So first you put in CLF, that's my smart model, and then we actually have to make it run again. So we're going to put in xtest, and we're going to put in the answer key. Now I can type in plt.show, and it should show a beautiful confusion matrix here with the actual labels. Now, why doesn't this show the labels of the actual things? That's interesting. Maybe I haven't imported one of my libraries properly, but maybe you can see the top should say iris setosa, I think, and the next one's versicolor. And so setosa should be 0. As you can see, there's 0 down here, and then the 0 is up top. So if 0 and 0 has a number inside, that means they guessed correctly. If you see 0, the row, and column 1, you notice that there's 0 predictions in there, which means this model's pretty good. Now there's 1 prediction here on the row that is number 1, and column number 2, it seems like they made 1 prediction, 1 wrong prediction. That's okay, we forgive you. So now let's try a different kernel and see if we can get a better better trained model. So we're going to do CLF2 this time, and we're going to do our same. I'm going to type a little bit faster so we can get through this. And kernel is going to equal RB, I think it's RBF actually. Yeah, RBF. I'm going to run that, and now I'm going to train the model. So we're going to do CLF2 dot fit, which means train, and then we're going to put in the X train and the Y train. Okay, with the answer key. Okay, it seems like it's saved, but how come it didn't show me what kernel? Interesting. CLF2, let me see. Oh, it doesn't show me the kernel. That's different than the last one. We're just going to see what happens here. So now we got to get our Y predictions. So let's make it YPred2, and let's make CLF2 write the test again by typing predict, and then we have to do xtest here. So now Y predictions 2 is the CLF2 writing the test, so predicting the answers of xtest. So now if we ran Y prediction 2 against the Y answers, so the Y test, then we'll see how accurate our model is. So we're going to try to plot another confusion matrix. You know what? I'll do it in the same thing here. So confusion, we already have this imported. Y test, oops, Y test and Y predictions, but Y predictions 2 we have to put in here. And let's see, this confusion matrix looks way better. Now no longer a 1, but it is now a 0. And just for fun, let's plot our confusion matrix. So plot confusion matrix CLF2 with X tests. So we got to make it train again. Y test, and then plot, oops, PLT, because we imported matplot library as PLT. Plot show, and then our confusion matrix now shows perfect. Now, just as a test at the end of this video, why don't you continue on, take a look to see what other kernels exist. So instead of kernel RBF or instead of kernel poly, put in another kernel and see what kind of response you get. A little hint, if you try another kernel, you might get completely wrong predictions, or a confusion matrix that looks like it made predictions of all versicolors. So this column here of 1, all of the predictions made by a certain kernel, I'm not going to tell you which one, it guessed all of them as versicolors. Let's see if you can replicate that. Thanks for watching, and I hope you enjoyed.